Statistics for data science. Our learning objectives today include defining statistics and the important terms related to them, explain the measures of central tendency and dispersion, discuss skewness and kurtosis, describe correlations and regression, and then discuss distributions. What is statistics? So let's say there's a sales prediction. A mobile company is planning to release a mobile phone, which would be an upgrade from the previous released phone. Now, based on the sales and customer feedback of their last phone, the company would like to know if this upgrade would increase sales or not. So how would they analyze that? Well, the company predicts the sales value by applying the rules of probability and statistics. So what is statistics? Well, statistics is the science of assigning a probability to an event based on experiments. It's the application of quantitative principles to the collection, analysis, and presentation of data. And statistic utilizes data from a population to analyze and draw conclusions. And based on these conclusions, the decisions taken. Now, that population may be a community, an organization, sales details, weather details, etc. And a statistician determine the quantitative models that suit a given type of problem. Then they decide the kind of data that should be collected and examined. Population and sample. So a population is the set of all measurements of interest to the study. And then a sample is a selected subset of measurements of a population that aims to represent that population. So in selecting a sample, in real-world situations, it's practically difficult to study the entire population. So for example, a company that manufactures mobile phones cannot interact with every single customer who purchased that product. And in such a case, the company would select a sample of the population. In order to apply statistics and study the population, we want to take a random sample. We want it to randomly represent the entire population. And a random sample is one in which each sample of a population has an equal chance or probability of being selected. And now what this does is it reduces the chance of human bias. And in turn, it hopefully makes it highly representative of the population. So if you only administered a survey in Boston asking people who their favorite NFL team was, that sample is very likely to be biased towards the Patriots. Whereas if you took a nationally representative sample, it will likely represent one of 32 teams. And so the process of selecting samples is called sampling. These units under study from a sample are called sampling units, and the number of units in a sample is called sample size. Types of data. Categorical data. This refers to data that can be classified into separate groups. It's also called qualitative data. And this data represents characteristics. For example, gender of a person can be male or female. It can also have numerical values to represent it, like 1 for male and 0 for female. Categorical data also can be further classified as nominal or ordinal. Now, data that can be measured quantitatively is called numerical data, hence why it's called quantitative data. So when values can be clearly separated from one another, then they're discrete. When data is essentially on a sliding scale, like seconds, it's continuous. Now we could technically say that time is fully continuous because you can continuously go down to such like nanoseconds. And so discrete and continuous data can be of two types, interval or ratio. So looking at these data types, we'll go through them. We have the categorical, nominal, and ordinal, and the numerical, interval, and ratio. And these are termed as scales of measurement. Measurements. So measurements are commonly termed as scales of measurement. Scales of measurement refer to the method in which variables or numbers are defined and categorized. And these 4 scales of measurement are nominal, ordinal, interval, and ratio. So let's go through these. A nominal scale. So categorical data and numbers such as Social Security or job designation represent nominal scales of measurement. So simply, I'm not sure you want to say that nominal don't have a numeric value when Social Security and job designation have a numeric value. Nominal values, you can think of it as name. They can't be added, subtracted, multiplied, or divided. So you can think of something like color. Red, blue, green, yellow is a nominal scale. Now, if there was some order to it, they would be called ordinal variables. Otherwise, they remain nominal. So, such examples include gender, such as male, female, transgender. There's no order to that. They're named, right? Eye color, blue, green, brown, hazel. types of houses, bungalow, duplex, or ranch. A type of pet, dog, cat, rodent, fish, or bird. So an ordinal scale of measurement refers to an ordered series of relationships or rank order. And this ordinal scale contains data that can be placed in some type of order. Now note, ordinal scales don't represent measurable quantities. And because of that, it's difficult to measure like the interval between those values. So you can think of it as a high school class ranking. The valedictorian's GPA compared to the salutatorian's GPA compared to the third person's GPA may not have the same distance between those two or between those three, but the ranking we know is first, second, and third. Social economic scales, like working class, middle class, and upper class. We know there's an order to these, but the difference, the discrepancy between these may be different. Or a Likert scale, where we talk about does somebody agree, strongly agree, disagree, strongly disagree with something. So an interval scale has measurements where the difference between the values are equal, and this difference is quantifiable and measurable. So let's say the Fahrenheit scale. The difference between 100 degrees and 80 degrees is the exact same difference as between 50 degrees and 70 degrees. Now note, interval variables don't have a meaningful 0 point. So 0 degrees does not mean there's actually no temperature at all. If a 0 ever becomes meaningful, then it's termed a ratio scale. Now in the ratio scale, 0 is meaningful. So in this scale, no numbers below 0 exist. It has an absolute 0. And the arithmetic operations can be performed on a ratio scale. So let's say we take the length of a piece of cloth that's measured in inches. Well, that measurement cannot ever become 0 or less than that, right? Because a negative length or a 0 length is not possible. It wouldn't even exist. So the difference between the four scales, we can say that nominal, ordinal, interval, and ratio all have differences between the values within those. Ordinal, interval, and ratio indicates a direction of difference, right? There's some sort of rank ordering to those. Interval and ratio indicates an amount of difference. It's quantifiable. And only ratio has an absolute 0 point. So it's clear from the table that the ratio scale satisfied all the four properties of scales of measurement. Descriptive and inferential statistics. So descriptive statistics describe or summarize particular sets of data. It gives an idea of the data in terms of the mean, mode, median, and range, the variance in the standard deviation, the skewness, count, maximum, minimum, a variety of other things, right? So when we're summarizing data, it becomes very useful, especially with a large amount of data, to use descriptive statistics. For example, if you have a population, the details within that city, such as age, sex, and income, it's practically impossible to study every single minute detail down at that minute level. So to infer any useful information from the data, it has to be summarized. And so descriptive statistics could be divided into following subcategories, such as the measures of central tendency, the measures of dispersion, using charts and graph, and then shapes of the distributions. Now, inferential statistics use a sample of the population to make comparisons or predictions on the population. For example, if you have survey data on the model of phone a person would like to purchase, then using inferential statistics, you can estimate that around 70% of people prefer any type of Android phone. So what are the methods of inferential statistics? Well, there's two main methods. The first is parameter estimation. So when we're estimating parameters, a parameter is any numerical value that characterizes the sample data from the population. And then estimating a parameter means that we're taking a statistic from your sample data and inferring the behavior of the population itself. We also have hypothesis testing. And so these are the tests used to evaluate research questions or an assumption of a population parameter. So what are the methods of inferential statistic? Well, with inferential statistic, using statistical models, we're trying to compare sample data to previous samples. And so the most commonly used statistical models fall under generalized linear models. And so some of these include t-test, ANOVA, and regression analysis. Frequency distribution and its diagrammatic representations. So frequency indicates how frequently the corresponding form of the character under study occurs in the collected data. Now, since it also indicates the manner in which the data is distributed according to the magnitude of the observations, it's called a frequency distribution. So an ungrouped frequency distribution could be represented by a bar diagram, counts of pink, lilac, white, and blue. We could use the data and take for the qualitative characteristics and represent those using something like a pie chart. So again, we have the same colors as a percentage of the total. Now in cases with a discrete variable, we might use a column diagram or frequency polygon to represent the frequency distribution. So as you can see with a column diagram and frequency polygon, it looks like the distribution is higher in the middle, around 5. Now we could also use group frequency distributions, which are commonly known as histograms. Now if you have discrete variables, you could represent those using a step diagram. If the data is continuous, we could even have a cumulative frequency of that continuous variable represented by an OG, which is this type of arch. Also with frequency distributions of a variable, with this infinite population, it's represented by a smooth curve, and this is the frequency curve of the variable. So when we're looking at clouds of distribution, the bell shape is the most common symmetric distribution. It's the most commonly used and understood distribution, and it is accepted in the majority of statistical models as a required assumption that data is evenly distributed around the mean. And this works for discrete and continuous variables. Now it's possible that we could have a asymmetrical bell shape. So we might have a single maximum that's extremely high. And because of that, we end up having this right tail. So this frequency density decreases on one side at a higher rate than the other. We could also have a J-shaped distribution. So this could be extremely asymmetrical. Here the frequency density is the maximum at one end of the range and decreases monotonically as the variable value changes from one end of the range to the other. Now a U-shaped distribution has a minimum frequency towards the middle of that range, so it's pretty much the opposite of that bell shape, symmetrical, and then the frequency gradually increases. And so this increase could be at the same rate or at different rates, and as the variable value changes, either to the left or right. And then in some situations, you could come across distributions with multiple maximums. So you might have a multimodal distribution, which signifies heterogeneity of the data. And this indicates that the data has been obtained from groups with widely different characteristics. Measures of central tendency. So a measure of central tendency is a summary measure that attempts to describe a whole set of data with a single value that represents the middle or center of its distribution. And there's three main components, three main measures of central tendency: the mean, the median, and the mode. And each of these measures describes a different indication of the typical or central value within that distribution. So for the mean, it's commonly referred to as the average. So for any set of data on the variables x, the mean is denoted by x bar, and it's obtained by dividing the sum of all observations by the total count of observations. The middlemost value of the set, where the elements are arranged in ascending or descending order, is called the median of a set of observations. So that median is essentially directly in the middle. And then the mode is the most commonly or most frequent occurring value within a distribution. Comparisons of measures of central tendency. So the mean and median are rigidly defined, and the position of the mode is somewhat similar to that of the median. All these measures are easy to interpret, they're not difficult to compute. So only the mean will directly depend on all of the observations. And so a change in any one of the observations will influence the value of that mean, which means the median and mode are not so sensitive. So when we think about outliers or anomalies within the data set, the mean is going to be highly susceptible, the median less so, and the mode likely not at all. And here we generally say that the mean is the best measure of central tendency. Measures of dispersion. So the range R of a variable is the difference between the largest and the smallest observations. So x sub n, the highest value, minus x sub 1, the smallest value. Now let's suppose a is the chosen average value of x for a given set of observations on the variable, and we could take the deviations x sub I minus a for all i's 1 through n into consideration while constructing a measure of dispersion of x. And then let's consider the absolute values, x sub I minus a. And you get this measure of dispersion by taking their mean, called the mean deviation of x about a. And as you can see below, It's computed as 1 over n times the sum of all absolute values of x sub I minus a. Then let's consider the deviations of the observations on the variable x from a chosen average a. So the mean of the square of the deviation is called the mean squared deviation about a and is denoted as s squared sub a. So this positive square root is an alternative measure of dispersion. It's called the root mean squared deviation of x about a. And it's computed as the square root of 1 over n times the sum of all values from 1 to n, where x sub I minus a is squared. Comparisons of measures of dispersion. So when we're talking about comparisons, the range and mean deviations are easy to interpret. The standard deviation may seem a little more difficult. Now the range is generally easy to determine, while the determination of the mean deviation, standard deviation, is more difficult. The range depends only on the two extreme observations and ignores the variation of the data lying in between. The mean and the standard deviation, on the other hand, properly reflect variations within the data. Compared to the mean deviation or the standard deviation, the range is highly affected by the presence of an extremely high or an extremely low value. And the standard deviation is surely the best of the three measures when it comes to algebraic treatment. Coefficient of variation. So the measure that expresses the standard deviation of x as a percentage of the mean is called the coefficient of variation of x. And it's computed as the standard deviation divided by the mean times 100%. Moments and quantiles. So moments refer to the data averages. The first moment is the sample mean. That's the mean of your data set. So if the number in the first cell is y sub 1 and the second cell is y sub 2, so for n numbers, the sample mean is given by the sum of all values of y divided by n. Now the second moment is the sample variance, and the higher moments are typically subtracted from the mean. So we take 1 over n minus 1 because it's a sample. With samples, we take away 1 in an effect to control for the population, and we multiply that times the sum of all I from 1 to n, whereby y minus x bar squared is equal to that sample variance. Now on quantiles, recall the median. So it's a value of x such that most half of the observations are below x and the other half are above x. Now if the proportion p is taken instead of half, then it would be quantiles with p, whereby p would fall between 0 and 1. Now the p quantile of a variable x is a value z sub p of a variable, such that the proportion p of the observation is below z sub p, and the proportion 1 minus p is above z sub p. So when we're looking to compute the p quantile, with p at the 1/4, 1/2, and 3/4 mark, there's 3 quartiles, z1/4, z1/2, and z3/4, denoted by q1, q2, and q3 respectively. Now, given a frequency table for a continuous variable, find the class intervals containing z sub p. If x sub 1 and x sub 2 denote the lower and upper boundaries, and f1 and f2 represent the corresponding cumulative frequency, then the p quantile z sub p is given by zp over x1 divided by x2 over x1, which is equal to np minus f1 over f2 minus f1. Or in other words, z sub p equals x1 plus np minus f1 all over f times c, where c is the width of the interval and f subscript 0 is the frequency. And note the p quantiles for a set of observations may not be unique. Skewness and kurtosis. So skewness is a measure of the deviation of frequency curve from symmetry of a frequency distribution. And skewed distributions can be classified as positively skewed or negatively skewed based on whether the longer tail of the distribution is towards the higher or lower values of the variables. So, on a pure symmetrical distribution, the mean, median, and mode will be in the exact same place. However, if there's positive skew, the mean is going to be biased by those higher values and will be skewed right. The mode will still stay at the highest point, and the median is slightly skewed to the right as well. With a negative skew, that long tail, the mean again is susceptible to those outliers, and so moves furthest away from the symmetrical distribution piece. The median moves a bit, and the mode stays at the highest point. So the measures of degree of skewness. A good measure of the degree fulfills the following criteria. So it should be a pure number. In other words, it should be free of the units in which the variable is measured. It should be 0, positive, negative for a symmetrical distribution, a positively skewed distribution, and a negatively skewed distribution, respectively. And it should vary between two definitive limits, say negative k to k, as the nature of a distribution changes from extremely negative asymmetry to extreme positive asymmetry. So for a symmetrical unimodal distribution, the mean is equal to the median minus the mode. So Q3 minus Q2 equals Q2 minus Q1. Now for a positively skewed distribution, the mean is greater than the median, which is greater than the mode. Thus Q3 minus Q2 is greater than Q2 minus Q1. And for a negatively skewed distribution, the mean is less than the median, which is less than the mode. And Q3 minus Q2 is less than Q2 minus Q1. Now for a symmetrical distribution, M sub 3, the odd order central model is equal to 0. For a positively skewed distribution, M sub 3 is greater than 0, and for a negatively skewed distribution, M subscript 3 is less than 0. Now kurtosis refers to the degree of steepness or pointedness of a distribution. So some distributions you'll see might be flat-topped, and some may be extremely highly peaked. Most distributions tend to be between these two extremes, not too peaked, not too flat-topped. So for two distributions with the same dispersion and the same degree of skewness, the one with higher kurtosis has a higher fourth power of deviations from the mean, which would result in a higher value of M subscript 4. Assuming that S is greater than 0, then B equals M divided by S, and ensures that the measure is taken into account that part of the peakedness of the distribution that's independent, whereas in addition to that part, is due to the variance. So we say for a normal distribution, B subscript 2 is equal to 3. This is the standard value. So any distribution with B equal to 3 is mesokurtic, which means moderate kurtosis. Now anything with B greater than 3 is known as leptokurtic or leptokurtosis. And anything with B under 3 is said to be platykurtic or platykurtosis. Correlation and regression. Now, regression analysis refers to the statistical methods that help in formulating models used to predict relationships among variables. And regression analysis broadly classified into two types. We have linear regression, used to explore the relationships between two variables, and multiple regression, which is used to predict one variable on the basis of more than one variable. Now, the first step to performing a linear regression would be to draw a scatter plot diagram. So, considering the following scatter plots extracted from different data sets, and you can see the lines fitting to each of these. In A, B, and C, they tend to be straight. D and E are curved. F tends to not have one. So in plots A, B, and C, because they're all close to a straight line, then we can also look at the slope. So A and B have a positive slope, which means there's a positive linear relationship of x on y, and the one in C has a negative slope. So when x increases on y, or when x increases for C, y decreases. Now with D and E, that relationship changes to curvilinear. And in F, it doesn't look like there's any specific relationship between the variables in the data. Now when performing a linear regression, for bivariate data, the conditional distribution of y given x indicates how the frequency for a given x is distributed over different classes of y. It indicates that the values of x are used for predicting the values of y. And now the curve derived from the conditional average of y given x against x is called the regression curve of y on x. And with a simple regression line, the equation of y on x is given as y equals a plus bx. So the constant a is the y-intercept of the line, represents the predicted value of y when x is equal to 0. We have x as the predictor variable, and y is the criterion. And then we have the constant b, which is the slope of the line, or weight of the variable, and indicates the rate of increase of the predicted value of y per unit increase in the value of x. So this is called the regression coefficient of y on x, and denoted as b subscript xy. Correlation. Correlation is a statistical technique that predicts whether and how strongly pairs of variables are related. Now, correlation coefficient, or R, ranges from -1 to +1. The closer R is to that +1 or -1, the more closely the two variables that we're looking at are related. So if R were close to 0, it means there's no relationship at all between the variables. If R is positive, it means that as one variable gets larger, the other gets larger. And if R is negative, it means as one gets larger, the other gets smaller. There's an inverse relationship. Now, a line of 1 or -1 means all data plots would fall directly on the line. But usually with real-world data, the accuracy would be anywhere from 0.3 to 0.9, depending on the models. Now, the Pearson correlation coefficient, also known as R, is defined as the covariance between x and y divided by the standard deviation of x times the standard deviation of y, where the standard deviation squared divided by n of x and for y are the variances of x and y respectively. And then the covariance between x and y, denoted as s x of y divided by n for the sample size, represents the covariance. And thus, when we actually square r, the value will be somewhere between 0 and 1. If r is not squared, it can be negative, and thus the value can exist somewhere between -1 and 1. Now, the relationship between regression and correlation coefficients of y on x says that the covariation between x and y divided by the variance of x distributions. So in probability theory, the normal or Gaussian distribution, you might hear Gauss or Laplace-Gauss, is a very common continuous probability distribution. And now normal distributions are important in statistics and are often used in the natural and social sciences to represent real-valued random variables whose distributions are not known. And a random variable with a Gaussian distribution is said to be normally distributed and is called a normal deviate. So when we look at distance measures are the mathematical methods for measuring the distance between two or more objects, and they help compare the objects from different perspectives. So we might look at similarity measures, which would range from 0 to 1. We might look at dissimilarity measures, which could range from 0 to infinity. And then we have our correlation measures, as we discussed, that can range from 1 to -1. And these measures are the basic building blocks for activities such as classification, clustering, and anomaly detection. So, with similarity and dissimilarity measures, these scores that describe the extent to which objects are similar and dissimilar to one another. Now, the table below summarizes the similarity and dissimilarity formulas. So obviously the similarity equals 1 if x and y are equal, and similarity is 0 if x is not equal to y on a nominal scale. In an ordinal measure, the similarity is equal to 1 minus the dissimilarity, and then with an interval and ratio, the similarity is equal to 1 over 1 plus dissimilarity, and respectively, the similarity is equal to 1 minus the dissimilarity minus the minimum dissimilarity divided by the max similarity minus the min dissimilarity. Alternatively, on a nominal scale, dissimilarity equals 0 if x is equal to y, and dissimilarity equals 1 if x is not equal to y. Now, on an ordinal scale, the dissimilarity is equal to the absolute value of x minus y divided by n minus 1, where n is the number of values. And d is equal to the absolute value of x minus y on interval or ratio scales. Now let's talk about Euclidean distance. So this is a classical method to calculate the distance between two objects x and y in the Euclidean space, which could be 1, 2, or n-dimensional. And this distance can be calculated by traveling along the line connecting the points. So when you think about Cartesian coordinates, if p subscript k from p1 through pn and q equals q subscript 1 through qn are the 2 points in the Euclidean n space, then the distance d from p to q, or from q to p, is given by the Pythagorean formula, where distance is computed as the square root of the sum of all values from 1 to n of pk minus qk squared. So Manhattan distance is similar to Euclidean distance, but the distance here between 2 points is kind of like being separated by building blocks in a city. You can't go through a building at a diagonal axis. So it's calculated by traversing vertical and horizontal lines in the grid-based system. And that's calculated, that distance calculated, by the absolute value of x2 minus x1 plus y2 minus y1 for the points x1, y1, and x2, y2. The Minkowski distance is a metric on the Euclidean space that's a generalization of both Euclidean and Manhattan distances. So what we say here is the distance is the sum from 1 through n of the absolute value of pk minus qk to the r power to the 1 over r power. And we can specify that where r is 1, it would then compute the Manhattan distance. And when r is 2, it would compute the Euclidean distance. And when r is infinity, it computes the supremum, the max. So, what are the key takeaways? Well, first, statistics is the science of assigning a probability to an event based on experiments. It's the application of quantitative principles to the collection, analysis, and presentation of numerical data. Now, population is the set of all measurements of interest to the study. A sample is a selected subset of that population to represent the population. The measure of central tendency is a summary measure that attempts to describe a whole set of data with a single value that represents the middle or center of its distribution. And skewness is a measure of the deviation or frequency curve from symmetry of a frequency distribution. Now, kurtosis refers to the degree of steepness or pointedness of a distribution, and regression analysis refers to the statistical methods that help in formulating models used to predict relationships among variables.